Hello, in this video we're going to talk about AP Chemistry's topic 2.6, resonance and formal charge. These two topics are related to one another, but they've got some differences, and we're going to deal with each of these separately. So first, let's start with resonance. And to think about resonance, we're going to look at an example of the carbonate polyatomic ion. First, we're going to draw the Lewis dot structure of this polyatomic ion, which means we need to count up how many valence electrons we have total in this structure. Carbon each have 4 valence electrons, and each oxygen atom has 6 valence electrons, and then we have 2 extra because of the charge. So 6 electrons, valence electrons times 3 is 18, plus 4 is 22, plus 2 more is 24. So let's go ahead and figure out what this structure is going to look like. So we'll draw the skeletal structure. Next, we're going to draw single bonds between each of the atoms. So 1, 2, 3, 4, 5, 6. Then we're going to fill in the octets on the valence electrons for the oxygens. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So at this point, we have all 24 electrons, valence electrons, accounted for. But if you'll notice, we do not have a full octet on every atom. The carbon has less than a full octet. So we're going to have to shift 2 of the electrons from one of the oxygens to make a double bond with the carbon. So let's erase those and put them as a double bond there. And now you can see that every atom has an octet. Since it's a polyatomic ion, I'm going to put brackets around it and put its charge on the outside. And this would be the Lewis dot structure. But wait, why would this oxygen and carbon have the double bond and the other oxygens, which have the same electronegativity, the same pull for electrons, only have single bonds? This is where the concept of resonance comes in. Through experimentation, scientists have found out that these 3 bonds actually all have the same amount of energy in them. The same energy is required to break each of those oxygen atoms. If this drawing was correct, then one oxygen would take more energy to break off than the other 2 single bonded oxygens. So this structure isn't quite correct because it doesn't show equal bonding between all the oxygens. So resonance is the idea that the other oxygens also get to share in this double bond. So I'm going to draw 2 more structures that are going to look identical, except the double bond is going to be on a different oxygen. So now you can see that the double bond is on the top oxygen rather than the right oxygen, and we still follow the octet rule. But again, why would this oxygen have the double bond and the other 2 not have the double bond? So I'm going to draw another structure, and sadly I've run out of room. Actually, I can just slide it over. I'm going to draw the same structure again, but this time I'm going to put the double bond on the right oxygen with single bonds on the other 2 oxygens. And so these 3 structures are ways of representing that the double bond is actually on all 3 of those oxygens, and single bonds are on all 3 of those oxygens. So they're actually sharing that double bond. This concept that the double bond is not isolated to any one of the oxygens is called resonance. In other words, that double bond is actually resonating, it's rotating around between the 3 oxygen atoms. Now, is that really what's happening? Probably not. But the double bond is being shared between all of the oxygens, and the single bonds are being shared through all the oxygens. So this is one way to represent this concept of resonance, that the double and single bonds are actually smeared across all 3 of the oxygens. So resonance is the idea that if you can draw equal Lewis dot structures between the atoms, then those equal structures represent resonance because there's an equal electronegativity between the carbon and oxygen atoms in this particular case. So what is the bond order on these oxygens? Well, let's calculate bond order on each one real quick. So if we look at this one right here, this one has a double bond, and so that would have a bond order of 2 because there's a double bond. This one would have a bond order of 1 because it's a single bond, and this one would have a bond order of 1 because there's a single bond. And then the same would be true for all the rest. Any place there's a double bond, there's a bond order of 2, and every place there's a single bond, there's a bond order of 1. But if resonance is going on, then that double bond is actually smeared across all 3 of these atoms. And so how can we calculate the bond order in a resonance structure? Since all 3 of these are equal, what we're going to do is we are going to take the total number of bonds that those 3 oxygen atoms are sharing and divide by the number of bonded atoms. In other words, how many atoms are bonded to the carbon that are sharing those bonds. So how many total bonds do we see here between the carbon and the 3 oxygens? Well, there's a double bond, a single bond, and a single bond. So that's 4 total bonds. How many atoms are sharing those bonds? Well, to the central atom, we have 1, 2, 3 atoms sharing those bonds to the central atom. So 4 divided by 3 is 1 1/3, or 4/3. So the bond order for this carbon and 3 oxygen bonds is 1 1/3. Each one has a single bond, but they also share that other bond, the double bond, which is basically a third to each of the oxygens. So experimentally, how do we know that this is the case? Well, when we look at double bonds between carbon and oxygen that are purely double bonds, they take more energy to break off the oxygen and carbon, to break the bond between carbon and oxygen, than it does to take the carbon and oxygen apart in carbonate. But if we have a carbon-oxygen single bond between 2 atoms, between a carbon and oxygen atom, that single bond takes less energy to break than the carbon-oxygen bond in carbonate. So somewhere in between the carbon-oxygen double bond and the carbon-oxygen single bond energy is the bond energy to break these. And so that's how experimentally we know that this model is a good representation of what's going on inside the carbonate ion and inside other structures that have resonance. So let's look at formal charge. For formal charge, we're going to look at carbon dioxide. Formal charge is how much electron density there is around each atom compared to the electron density it normally has. So let's draw a Lewis dot structure for carbon dioxide. If you follow the rules for drawing Lewis dot structures, this structure is a valid structure. But another structure, is this. This is a valid structure too, according to the Lewis dot structure rules. Everybody has an octet and there's the right number of valence electrons. And then why would this oxygen have a triple bond and this one only have a single bond? So there's actually another structure that looks like this. So there's 3 different structures for carbon dioxide. And this is resonance because the electrons can shift around. But one of these structures is way more stable than the other structure. In other words, these are not equal structures when it comes to electron density. So what we're going to use is what's called formal charge. And the way that we calculate formal charge is for each atom, we take the number of valence electrons that the atom has, we subtract the electrons in double bonds, in lone pairs, sorry, the electrons in lone pairs, and we subtract half the electrons in bonds. So we're going to do this for each atom. So let's do this for this oxygen atom right here on the left-hand side. We're going to calculate the formal charge of every atom in the structure. So if we take this oxygen atom over there on the right-hand side, the formal charge is equal to the valence electrons that an oxygen atom has. Oxygen normally has 6 valence electrons. There are 1, 2, 3, 4 electrons in lone pairs. So we're going to subtract 4 electrons in lone pairs. And then there are 4 electrons in the bonds. So we're going to take half of those, which is 2. And when you do that math, you get a formal charge of 0. So this oxygen atom has a formal charge of 0. Now let's do the carbon atom in the middle. The formal charge of the carbon atom in the middle. Carbon has 4 valence electrons. There are no electrons in lone pairs on that carbon atom. And there are 2, 4, 6, 8 electrons in bonds. So we're going to take half of that, which is 4, which gives us a formal charge of 0. Let's look at the other oxygen atom. The last oxygen atom is exactly the same as the first oxygen atom, so it has the same formal charge, 0. What that means is these atoms each have the electron density around them that they normally would have as an element. Carbon normally has 4 electrons around it, and through the sharing of electrons, it still has about 4 electrons around it in the valence shell. Oxygen normally has 6, and it still has 6 valence electrons around it if you take in consideration these are being shared. So formal charges of 0 are more stable. Atoms are likely to form bonds that give the atoms a formal charge of 0. Let's try this next structure right here, our middle structure. If you'll notice, this oxygen atom has a lot of electrons around it. So let's calculate its formal charge. So the formal charge of that left oxygen is equal to the number of valence electrons. Oxygen normally has 6 valence electrons. The electrons in lone pairs, there are 6 electrons in lone pairs, and half the electrons in a bond. So 2 electrons in the bond, so -1. So the formal charge on that atom is -1, meaning that it has 1 extra electron around it than it normally would have when it was by itself. It has a higher electron density than it would if it was just elemental oxygen. Let's do the carbon atom. This is the formal charge of the carbon atom. There are 1, 2, 3, 4, 5, 6, 7, 8 electrons in bonds. So carbon has normally 4 valence electrons. Half of 8 is 4. And there are no lone pairs. So the formal charge on this carbon atom is 0. Our last structure is the other oxygen on the right-hand side, this one. And oxygen normally has 6 valence electrons. There are 2 electrons in a lone pair, so -2. And then there are 6 electrons being shared, so half of that is 3. So 6 minus 2 minus 3 gives us +1. So the formal charge on this oxygen is +1. So if you'll notice, we do not have 0 formal charges in all the atoms. We have a negative formal charge on one oxygen, we have no formal charge on the carbon, and we have a positive formal charge on the other oxygen. That means that this structure is not as likely as the first structure with all formal charges of 0. Typically, structures that have formal charges closest to 0 are going to be the most stable structure. So our most likely candidate for the structure of carbon dioxide is this one. If we calculated the formal charges over here on the right-hand one, they would be very similar to the formal charges on the middle one, because it's basically the same structure, just flipped. So formal charge allows us to figure out the most likely candidate for the most stable structure for a compound. I'm going to stop there. If you have any questions about this, please talk to me. I'll be happy to help you out. Good luck with your studies.